RA0 group provide efficient cost-effective solution in ultra-low power range. It's provide up to 32 MHz of CPU performance using ARM Cortex M23. It has embedded flash memory up to 64 KB. It is excellent choice for low-budget embedded devices. In this project, I will demonstrate how to use user LEDs present on FPB RA0E1 board. Create a new project in Escape Studio by clicking on this file icon, then select New, then select Renaissance C++, then select Renaissance RA project. A new dialog box will appear. You can give name to your project here. After giving name to your project, click on Next button. Here you can select FPB RA0E1 board from this drop-down menu. After selection, click on this Next button. Here select Executable and No Autos option. When you select executable, IDE will add low-level implementation of processor initialization code, startup code, interrupt vector table, NVIC controller configurations, and bootloader or reset handler. Executable programs are directly compiled into .hex, .bin, or .elf files that can be directly run on hardware devices. On the other hand, static library are collection of pre-compiled code that can be linked into an application at compile time. It's typically contain usable function, classes, or code module. When we compile static library, the output is .lib or .a file. We cannot run static library on hardware device. We need to link it with executable at compile time. Now select bare metal minimal and click on finish button. A new project is created. Open FSP configuration file. In FSP configuration file, a default GPIO stack is already created according to FPB RA0E1 board. Now click on Pin tab, then expand P0. As you can observe here, P08 is already configured as LED1 pin and P09 is already configured as LED2 pin. Now I will show you how to add a new pin configuration according to custom design board. Click on Manage Configuration. A new dialog box will appear. Click on Add button. You can give any name to your new configuration. From this drop-down menu, you can select any configuration and change pin setting according to your desired project. Only the pin required for flashing the board are configured. Other than that, no pin settings are defined. In new configuration, you can define pin setting according to your board design. As I am using FPV RA0E1 board, now I will show you how to use your custom pin configuration with GPIO stack. This variable name here should be a standard C variable name for all pin configurations. Click on Stack tab. Now click on GPIO stack. Then open Properties. Here you can give name of your pin configuration. I will continue with default pin configuration as I am using FPB RA0E1 board. Click on Generate Project Content. Open SRC folder. Then open hall entry.c file. In this file, hall entry function is present. User application will start from here. We can write our user application in this function. Define a while one loop here. You can take help from Developer Assistance tab for API calls related to GPIO stack. This drop-down menu has different API calls related to GPIO stack. Expand Developer Assistance tab and drag and drop PinWrite API to your hard entry.c file. We will use PinWrite API in our program. To use a particular pin, we need to give its name in this API call. By default, in FSV configuration file, it was given as LED1 and LED2. We will use those names here. Second argument in this API call is pin level. We can define pin level by using a predefined macro in FSP. It is BSP underscore IO underscore level underscore high to make this pin high. If you hold control button and click on function name, it will take you to its implementation. Here you can observe the low level implementation of pin write API call. According to IO level, bits are clear or set in specific registers. You can hold control button and click on variable to further investigate where it is defined. Here you can study implementation of pin write API call. Here you can observe which register bits are set or clear in order to make pin high or low. We can check status of these API call by using FSP underscore ER underscore P variable to check whether the API call was successful or not. Use assert function to make sure API call was successful. Copy pin right API call and paste it here. Change pin level to low. Add delay using RBSP software delay. I will create a 1000 millisecond delay. First argument in this API call is an integer number. Second argument in this API call is a predefined macro in FSV which will convert this integer number to milliseconds. You can press Ctrl plus spacebar to get suggestions related to predefined macros in FSV. Now I will program LED to copy this print write API call from here and paste it here. Now change LED1 to LED2. Again create a 1 second delay. Copy this API call from here and paste it after LED2 pin write API call. Copy this API call for LED2, paste it after delay and change its IO level to low. In Project Explorer tab, click on your project name, then click on this hammer icon to build your project. Right click on your project name, then select Debug As, then select Genesis GDB Hardware Debugging. After that, IDE will ask you to launch Debug Perspective. Click on the switch button to launch Debug Perspective. In debug mode, click on this resume button twice. Now we can test our program on physical board. As you can see, LED1 and LED2 are blinking for 1 second alternatively on FPB RA0E1 board.